This program uses ratios of numbers. Ratio is a convenient word used to express a simple idea, one number divided by another. For example, we say the ratio of 8 to 4 is 2 because 8 divided by 4 is equal to 2. The ratio of 5 to 20 is 0.25. The ratio of 100 to 400 is also 0.25. For any numbers a and b, a divided by b is called the ratio of a to b, provided, of course, that b is not 0. In this program, we use ratios to compare various quantities, such as lengths of line segments, areas of plane regions, and volumes of solids.
We learn to recognize objects by shape and size. We say the Earth and the Moon are round because each shape is spherical. And we describe the size of a spherical object by its diameter. This scale model of the Moon has a diameter of 6 feet. It has the same shape as the Moon, but the Moon is much larger, with a diameter greater than 2,000 miles. All around us, we recognize objects that have virtually the same shape, but come in different sizes. For example, families of seashells come in different sizes, but have very nearly the same shape. The little pyramid on the right is dwarfed by the giant pyramid of Cheops, but it has the same shape. When they design new automobiles, engineers build scale models to check airflow and measure wind resistance. And some people are fascinated by model airplanes. They're used as toys and as collector's items. This scale model of the Tacoma Narrows Bridge was built to learn why the full-size bridge collapsed. In the classic science fiction thriller Manhole Monsters, invaders from outer space have enlarged small garden creatures more than 80 times their ordinary size. We'll see how to defeat such monsters with a little mathematics. Questions about shape and size can be answered using geometry. Early civilizations used geometry not to study giant insects, but to build magnificent temples. The Greek mathematician Thales and the Pythagoreans studied geometric figures that have the same shape. Eudoxus invented the theory of ratios, and Euclid put it all together in books 5 and 6 of his Elements. Today, we say that objects with the same shape are similar, from the Latin word similis, which means alike. Similarity is basic to all measurement. Every manufactured object, from a microchip to an aircraft, starts with a scale drawing or model which reproduces the same shape at a smaller or larger size. A globe is supposed to be a scale model of the Earth, but in this globe, vertical distances have been exaggerated about 12 times to reveal features such as mountain ranges. If the Earth was similar to this globe, Mount Everest would rise 348,000 feet above sea level, instead of its true elevation of 29,002 feet. In a true scale model this size, the surface would be quite smooth, with Mount Everest only 1/16 of an inch high. Maps of flat surfaces reduce all distances in the same ratio, but don't change shapes. In this street map of Washington, D.C., 1 inch represents 4/10 of a mile. We also use similarity when we test a model in a wind tunnel to learn how the full-size craft will respond under the same conditions. How can we construct a figure with the same shape as another? Let's start with one of the simplest shapes of all, a triangle. It has 3 sides and 3 angles. Can we change this to another triangle without changing its shape? Sure, just move it around or flip it over. All these have the same shape and the same size. We call them congruent. To double the size of a triangle without changing its shape, we use our trusty expando ray and set the dial at 2. Aim at a point inside the triangle and expand all distances from this point by a factor of 2. You get a triangle twice as large that has the same shape. You can also aim at a point on the boundary and expand all distances from this point by a factor of 2. Again, you get a triangle twice as large. The point you aim at is called the center of scaling. It can be inside the triangle, at a vertex, or anywhere in the plane of the triangle, or even outside the plane of the triangle. You always get a triangle twice as large, but with the same shape. The 2 triangles have the same shape because the angles have not changed. The length of each side is multiplied by 2, so the ratio of the lengths is equal to 2. All ratios of lengths of corresponding sides are equal to 2. This ratio is called the scaling factor. Sometimes we indicate corresponding parts by using primes. For example, A prime corresponds to A, B prime to B, and C prime to C. If we expand by the scaling factor 3, we get a triangle with sides 3 times as large. Again, the angles don't change, and the lengths of corresponding sides have the same ratio. The same is true if we shrink the lengths to any smaller size, for example, 1/2. In general, when we multiply the lengths of the sides of any triangle by a scaling factor, we obtain a new triangle whose angles are the same, ratios of corresponding sides are equal to the scaling factor, and the triangles are called similar. Scaling a triangle changes all line segments by the same factor. For example, look at corresponding altitudes of these 2 similar triangles. Each altitude divides the original triangle into 2 right triangles. These 2 right triangles are similar, with the same scaling factor as the original triangles, so corresponding sides have the same ratio. Therefore, the altitudes have the same ratio as the lengths of the corresponding sides. The same is true for each of the angle bisectors. And for each median, the line segment from a vertex to the midpoint of the opposite side. These examples illustrate a general property of similarity. Scaling changes all line segments by the same factor. People have used similarity to solve problems in real life ever since ancient times. For example, in the 6th century BC, Thales used similar triangles to find the height of a column by comparing lengths of two shadows. Here's how he might have done it. These two right triangles are similar because corresponding angles are equal. So, ratios of corresponding sides are also equal. As the sun moves through the sky, the shadow lengths change, but their ratio does not change. At a certain time of day, the length of this shadow is equal to the height of the staff. Therefore, at the same time of day, the column shadow has length equal to the height of the column. So all Thales had to do was measure the column shadow at the right time of day. Legend has it that Thales also used shadows to find the height of a pyramid. This was more of a challenge. He couldn't see the base of the big triangle inside the pyramid. So he placed markers here and waited until later in the day when the staff shadow was stretched by an amount equal to its height. These two triangles are similar, so corresponding ratios are equal. The height of the pyramid is equal to the change in the shadow length. Here's another application. We can use similar triangles to show that the sum of the angles in any triangle is 180 degrees, also called a straight angle. If you extend these two sides, these two angles are equal. Now shrink the triangle to a smaller size. The angles don't change. Shrink it even further to a single point, and you see that the three angles do indeed form a straight angle. That's all there is to it. Similarity can be applied to more general figures. For example, if we scale a polygon, we obtain a new polygon. Corresponding angles are equal, and lengths of corresponding sides have the same ratio. Any two polygons with both of these properties are called similar. Starting with any shape, a similar shape can be made by scaling, translation, rotation, or mirror reflection. When similar shapes are moved around like this, it may take a moment to figure out the corresponding sides. The shape of a curved figure is also preserved by rotating, scaling, or taking mirror images. These three figures are similar. Scaling, translating, or rotating a circle always gives us another circle. We can also scale solid objects. If one solid object is obtained from another by scaling, the two objects are similar.
The Jet Propulsion Laboratory near Pasadena, California, built the scale model of the spacecraft Voyager, as well as the full-size replica, which is 15 times larger. In this blueprint, the scale is 1:16. The shape of the actual spacecraft is the same as in the drawing, but all linear dimensions are multiplied by the scale factor 16. This length, for example. The lengths of the trusses, the widths of the panels, all can be found by making measurements on the drawing and multiplying by 16.
Ratios of lengths in the same figure are called internal ratios. Form the internal ratio of two sides in the same triangle. Form the internal ratio of the corresponding sides in the larger scaled triangle. The scaling factor cancels, so the internal ratio of the two sides in one triangle is equal to the corresponding internal ratio in the other triangle. And the same is true for any two lengths. Corresponding internal ratios in similar figures are equal. When you enlarge a snapshot to portrait size, all internal ratios stay the same. That's how we recognize it as the same person. See what happens when we change the scale in one direction only. Some internal ratios may also change. This equilateral triangle has three equal sides of unit length. Its perimeter, the length of the boundary, is equal to 3. If the figure is scaled by a factor, for example 2, the perimeter is multiplied by the same factor, giving a perimeter of 6. If the scaling factor is s, the perimeter is multiplied by s. For any triangle, the perimeter is the sum of the lengths of its sides. If we expand or contract a triangle by a scaling factor s, the perimeter is multiplied by the same factor. The same is true for perimeters of any two similar figures, even if they have curved boundaries. Expanding or contracting by a scaling factor multiplies the perimeter by the same factor. Let's apply this idea to a circle of diameter 1. Its perimeter, also called its circumference, is about 3.14. Scaling by a factor d gives us a similar circle whose diameter is d, and the circumference is multiplied by d. The ratio of circumference to diameter is the same for all circles, large or small. This constant ratio, which we'll see in another program, is denoted by the Greek letter pi. The circumference of a circle of diameter d is equal to pi times d. In terms of the radius, the circumference is 2 pi r. What about areas of scaled figures? Start with a rectangle. Its area is the product of its base and altitude. We can scale by a factor s in 2 steps. First, stretch the rectangle by a factor s in the vertical direction only without changing its base. Then stretch in the horizontal direction without changing the altitude. Vertical stretching multiplies the area by s, and horizontal stretching multiplies by s again. So, altogether, the area of the original rectangle gets multiplied by s squared. Scaling a rectangle by a factor s multiplies its area by s squared. The area of a triangle is half that of a rectangle with the same base and altitude. So if the triangle is scaled by a factor s, its area is multiplied by s squared. Every polygon can be divided into triangular pieces, and its area is the sum of the areas of all the pieces. If the polygon is scaled by a factor s, the area of each triangular piece is multiplied by s squared. So the same is true for the area of the scaled polygon. Finally, any plane figure with a curved boundary can be approximated by polygons. If the figure is scaled by a factor s, the area of each polygon in the approximation is multiplied by s squared. So the same is true for the area of the curved figure. Scaling changes area by the square of the scaling factor. For example, if a circle of radius 1, called a unit circle, is scaled by a factor r, you get a circle of radius r. The region bounded by the circle is called a circular disk. The area of any circular disk is equal to the area of a unit disk times the square of its radius. In another program, we'll learn that the area of a unit disk is our old friend pi, so the area of a disk of radius r is pi r squared. What do you think happens when you scale a three-dimensional object? For example, if you double the edge of a cube, its volume is doubled 3 times, once for each dimension. And the area of each face is doubled twice. If you scale by a factor s, linear dimensions are multiplied by s, surface areas by s squared, and volumes by s cubed. And the same is true for a pyramid, a sphere, or any three-dimensional creature.
Similarity explains why the heart of a hummingbird beats about 16 times faster than a human heart. The heart rate depends on the ratio of surface area, through which body heat escapes, to volume of blood, which keeps the body warm. For a hummingbird, this ratio is about 16 times that of a human, so the bird's heart has to beat about 16 times as fast. Similarity also explains why insects cannot grow large enough to become monsters. If we enlarge a praying mantis to be the size of a horse, the scaling factor is about 80, increasing its volume and hence its weight by a factor 80 cubed. But the strength of the legs increases like their cross-sectional area by only 80 squared. The poor creature would collapse on those spindly legs.
And that shows how easy it is to destroy monsters with a little mathematics. In this program, we've